Awesome. All right, so here we are with our section 8.3 notes. We're talking about the geometry of complex numbers. And we've talked about how to go from polar, that's an r and a theta, into rectangular, xy. We've talked about how to go from rectangular, xy, into polar, r and theta. And what we have today is how we're going to be going from complex numbers to polar coordinates. So we're looking for how we get this complex number, an a plus bi. And we're going to see how we can convert that into polar. Now you may remember from our very first section in this chapter, Section 1 was all about complex numbers, and we saw how to convert a complex number like 2 minus 3i into rectangular coordinates. All we had to do was take the a and the b portions, and they became our x and y. So if we see how we're going to turn our complex number into rectangular coordinates, we're going to just use our same process that we had from 8.2 to go from rectangular now to polar. Instead of memorizing a whole new batch of formulas, I think this makes a little bit more sense for us. So we start first by writing our complex number in rectangular coordinates here. Let's go ahead and graph that. Get a little visual of where we are here in quadrant 4. And then we'll use the exact same process we had in 8.2 to convert to polar. Our radius, square root x squared plus y squared. Our x is 2. Our y is negative 3. 4 plus 9, let's see, so we're looking at a square root of 13. And again, using our same formulas from section 8.2 to find our theta, we're going to use our inverse tangent of y over x. Y is negative 3, x is a 2. All right, let's see. I am in degree mode, doing my inverse tangent of negative 3 over 2. My calculator is telling me negative 56.3 degrees. Let's stop there and make sure we have it just exactly right. I'm going to put my pen into its standard position. Looks like we're moving downward, negative 56 degrees. That puts me looking like this. Am I going to have a positive or a negative radius value? Positive. Awesome. So I'm going to choose a positive 13. So since our angle is negative 56.3 degrees, our r would be positive. That means we're going to use a positive root 13. This would work out perfectly if we had no restrictions at all. This could be our solution. But if we read very carefully what our restrictions were in the problem up here, it needs a positive radius and an angle that is, first of all, in radians and second of all, positive. So let's see how we're going to go about doing this. Since our angle has to be from 0 to 2 pi, we have to spin our angle to add a full circle. So I'm going to add 360 degrees, or if we were in radians, I could add 2 pi. So I need to first start by spinning this so that I have a positive angle measure. Let's add 360 degrees. Negative 56.3 plus 360. Looking at a positive 303.7 degrees. Not quite set to go because it also tells me I need to convert this to radians. So now I'm just going to multiply this by, let's see, I want it in radians. I have it in degrees. So I'm going to multiply by pi over 180. And it's okay to go into decimals at this point. We don't have to keep it in exact radians with a pi anymore because We already have a decimal here in our degrees. So I'm going to take that 303.7, multiply it by pi, divide it by 180, and I'm finding a radian measure of about 5.3 radians. My radius was positive, so I didn't have to change that. That was what told me I should add a whole circle because I wanted to keep my radius just how it is. So now I have a radius of a positive square root of 13 and 5.3 radians. I have met all my restrictions: positive radius, positive radians, and polar form. All right, to continue onward, when we're thinking about this, there is actually one more form, but you may have noticed that I don't have it up on the windows. On our windows, we have polar, rectangular, and complex form. There's a fourth form called trig form. Please box this in for me. Trig form keeps it in terms of a trig function. And I didn't put it up as its own category because it's so similar to polar form that it's not even really worth having its own name. And you guys will see what I'm talking about. What we're going to do is we're going to squish polar form and complex form together. But once we have it in polar form, we are in fantastic shape. One thing we always have to be aware of, though, is to make sure the radius is positive. In trig form, radius must be positive. And it separates it, instead of just calling it radius and theta. You know, mathematicians, they have to add more words than is ever necessary, into calling it an argument and a modulus. The argument is just like the theta. So think of argument is A, argument is the angle. The modulus is just like our radius, just like R, but it has to be positive. So we'll just check like we did up here. We'll just check that the radius is positive if we need to rotate 360 degrees or if we need to rotate 180 degrees. We'll do it. Whatever we need to do to make sure that radius is positive. So we've talked again once more about how we can convert a complex number to a polar coordinate just by going to rectangular first, double checking, and to separate it into an argument and a modulus, we just had to make sure that that modulus was positive, that radius was positive, and we were in great shape. So here is how we go finally into our last form, our trig form. Box this in for me right here. Once we have a positive radius, the modulus, and we have the argument, the angle, we're just going to plug everything into this form. We're not going to calculate sine and cosine. We're going to leave it in terms of sine and cosine. That's why it's called trig form. It has trig formulas in it. All right. So what we're used to is going from polar to rectangular. Our polar coordinates are theta to rectangular. We found that our x and y, x was r cosine theta, y was r sine theta. This is how we made this conversion from polar to rectangular. We're going to take this exact kind of format and just rearrange things a little bit. Do you see how they both have an r in them? It's almost like we're going to factor out an r, put that out in front. And then just like we have a plus bi, remember I said that it's almost like we're mushing together polar and complex. We're going to have an a plus bi form, kind of something like that, but what we're going to do is put that I in front here. So I'm going to actually have a sum of two things plus an I. One thing plus an I something. And then that cosine and that sine just fill in what we have. What we end up with is r times the quantity, cosine theta, plus I sine theta. And remember that radius has to be positive. So let's give it a shot here. We have a complex number, -2 minus 2 root 3. We want to go into trig form. First, we go from complex to rectangular. -2 comma -2 root 3. -2, -2 root 3. We're somewhere down in quadrant 3. Our next thing is to go from rectangular into polar. Radius equals square root of x squared plus y squared. I'm not sure how many times I've said that today, but it's probably feeling like a whole bunch. -2 squared I know is 4. -2 root 3 squared. Well, the -2 squared turns to a positive 4. Root 3 squared is 3, so 4 times 3 is 12. We end up with 4 plus 12 underneath our square root. Square root of 16, positive or -4. I'm going to keep this in mind because I still have a decision to make. I still may need to adjust this. I know I need it to be positive eventually, but I need to keep this in mind that right now I'm not sure which. To find our theta, tangent -1 y over x. So inverse tangent -2 root 3 over -2. Well, hey, that's pretty cool. -2's cancel out. What angle has a tangent of square root 3? Check it out on your calculator if you need to. What do we have? All right. And did your calculator give you it in a negative like that? Because I'm curious. Awesome. All right. So our calculator is going to give it to us as a positive 60 degrees. And perhaps you were saying that you knew that we needed to switch that around, because if I use this, what I have right now, this positive 60 degrees, I would need to move towards the eraser part of my pencil to get down into quadrant 3. So I would have -4 and 60 degrees. But remember, for trig form, this has to be positive. So I have to somehow change this to become positive. That means I need to rotate my angle. Instead of just being 60, I need to rotate farther around. So instead of just rotating up to 60 here, I need to add 180 to it. Add 180 to that 60. That turns my radius to be a positive number, and my angle goes up to 240 degrees. I've converted this so I have a positive angle measure. I'm finally ready to put this into trig form. I'm going to go right up here so that I see what I have. First things first, my positive radius hangs out front by itself, 4. Cosine of the angle, cosine 240, plus I sine of my angle, sine of 240. This is my trig form. I do not simplify it. I don't calculate. I don't do anything else to it. I leave it just like this. So you see how nicely we go from complex to rectangular, and how nicely we can go from polar to trig. It's just this idea of going from rectangular to polar and polar to rectangular that takes a little bit more calculation.